Sorry, don't get misled by the first slide, because I have opened another slide which I had modified for HBNI.
No problem.
This file is open. So I think we can go here straight.
Okay. Yeah.
So shall I start?
Just a minute. Rohit? Sir, can start? Yes. Okay, sir, you can start now.
Okay, thank you so much, Dr. Haripal Das, and all the organizers of this course. And I'm really thankful to all of you for giving me this opportunity to interact with several scientists of various organizations. So this course is actually, I am covering the module 8 of this advanced NMR spectroscopy. My basic coverage will be on MR imaging. And during this course, during these lectures over next 1 month, I will be covering basics of NMR, historical background of NMR physical principles, their relaxation times, and other NMR parameters. Then basics of concepts of magnetic resonance imaging, magnetic field gradients and spatial localization in MRI. Then image formation, K-space and rapid imaging. Then conventional MRI and factors affecting image quality in contrast. Then topic 4 will be measurement parameters and image contrast, T1 weighted image, T2 weighted image, proton density, and other type of images. Then I will go on to MRI pulse sequences, which are very important, which decide which contrast you want to produce using MRI. And then we'll cover basic pulse sequences like spin echo and gradient echo, going on to inversion recovery and its variants, then fast sequences to speed up the image acquisition, and then ultra fast sequences like echoplanar imaging. Then unit 4 will comprise of NMR spectroscopy and MRS. This will be in vivo NMR spectroscopy. We will be covering most of the times. We will talk about only on the brain, and where we'll have basics of NMR spectroscopy, in vivo, in vitro, and ex vivo spectroscopy, then volume localization and pulse sequences in MRS, then multinuclear spectroscopy, and then clinical and cognitive research applications of MRS, then NMR metabolomics. And then unit 5 will be very important. That is a hardcore, the techniques on advanced MR imaging techniques, like how do you create morphological images, how do you do functional imaging of the brain using MRI and resting and task-based fMRI. Then we'll go on to diffusion imaging and diffusion tensor imaging, which are very important in studying the microstructural, organization of the brain. Then we'll go to biomedical and neurocognitive applications of advanced MRI techniques. Then MRI application in yoga and Ayurveda. And then we'll also have some applications in neuropsychiatric and neuroendocrine disorders. And then we'll also, in brief, discuss imaging techniques in neuroscience. What are the other imaging techniques? Then we will have unit 6 on MRI instrumentation, MRI quality assurance, MRI artifacts, and safety considerations in MRI. And then we'll briefly talk about some of the softwares which are widely used for the processing of MRI and MRS data. And this is in tune with your syllabi which you had given me. So this will cover all the topics what you had mentioned in the syllabus for this course. So at the end of the course, we expect the participants to understand the basic concepts of MRI and advanced MRI techniques, understanding the terminology used in MRI, fMRI, DT, and details of instrumentation, and then appreciate the effect of various pulse sequences and the sequence parameters on image quality and contrast, understanding the concept of design and fMRI task paradigms for doing functional imaging experiments, ability to design and conduct fMRI experiments for your research questions, working knowledge of MR spectroscopy and in vivo, in vitro, and in vivo applications, appreciate the potential of MRI and its applications in biomedical and cognitive research, working knowledge of the most commonly used softwares for processing of MRI data, observe the quality assurance and safety measures in handling MRI machines, then preliminary knowledge about the formation and assessment of specification for the MRI procurement process. So I think this is the deliverables from this course over next 12 lectures. So going to the topic, like magnetic resonance imaging or NMR imaging is like any other imaging techniques which you all know, whether it's computer tomography or sonography. It is another technique which is non-invasive, and it can be used in variety of specialities in medical science. And the advantages of MRI are, it has a excellent soft tissue contrast, and contrast is very flexible. You can choose by varying the parameters, NMR parameters. You can vary the contrast of the images to get a diagnostic and useful information from the images. It is completely non-invasive, and it does not use any ionizing radiation, so it is safe for human use, and you can repetitively do experiments using MRI in healthy subjects as well as on patients. You can have a slicing in any arbitrary scan plane without moving the patient. Is by switching the gradients in different orientations. Without moving the patient, you can cut slices in any. And the most important advantage of MRI is it has a multi-parameter contrast. If you look at the other imaging modalities like X-ray, CT, or ultrasound, they only have one contrast parameter. Like for instance, for CT, there's only the X-ray attenuation coefficient of the tissues which decide the contrast in CT scanning, and in ultrasound it is only acoustical impedance of the tissues which decide the contrast. But if you look at the MRI, it has about dozen parameters, which makes it very powerful, but a very complex technique to work with. And there are certain challenges. We are still discovering many more contrast mechanisms in MRI, and the faster we are also trying to speed up the imaging so that you can do a snapshot imaging of the whole organ or the brain in some some specialized cases. So if you look at the MRI contrast
Hello,
parameters,
Professor Kushro. Just a small interruption. There is a patch at the corner. Can you see that? Can you pull that aside?
My the pictures.
Yeah, the right corner top. Yeah,
that picture.
there's a patch. Can you just move aside or
Shall I close them?
Minimize it.
you can minimize that if possible? What is that patch? I don't know.
Okay.
No, it is.
Yeah.
Yeah, it is okay. Maybe it is
Okay.
at the bottom. Yeah.
So if you look at, if you when you acquire an image, the image is a function. The signal is a function of so many parameters, which you can see on the screen. The proton density is number of active nuclei which are participating in the experiments. Then T1 relaxation time, T2 relaxation time, T2 star relaxation time, the diffusion of water within the image, the perfusion of the blood in the capillary blood flow, then bulk flow. You can also look at the bulk flow and you can calculate the flow velocities of the different liquids, particularly CSF and blood, for angiographic applications. Then chemical shift is another parameter, which is a contrast parameter, which can create image from a fat or also from the water or any other tissue. Then magnetic properties of specific molecules like hemoglobin. These are called susceptibility imaging and fMRI. These have special applications. So any image which you create will have all these ingredients inside. Now it is the job of the scientist who is working on the machine to see and to look for specific information out of these all parameters. So you have to create a image which should be dominated by one of these parameters. Is it okay? Hello?
It's okay, sir. Go ahead. It's fine.
Okay. I don't know. I'm again stuck.
Slide is not moving.
No.
Okay.
Maybe solution.
Okay. So now, based on these parameters, there are different techniques which have been developed. And if you look at the different contrast parameters, you have a fMRI in bold sequences, which are used for the functional mapping of the human brain. When the brain is functioning, how to map the areas responsible for a particular function. The resting state fMRI is another very robust techniques to see the resting state interconnectivity of the different networks in the brain. And when there is a disease process, the network connectivity in the brain gets affected, which you can measure using resting state fMRI. When there's a aging or a disease process, there's a change in gray matter, white matter, and other components of the tissues, and then you can assess the changes in the gray matter, white matter volumes using VBM, voxel-based morphometry, and you can also create an image which shows you change in the relaxation times in different regions of the brain due to a disease process. Then you can use a DTI or diffusion imaging techniques to look at the diffusion processes which are happening in a tissue, and when the disease sets in, the diffusion patterns change in the diseased tissue, which you can measure using the diffusion weighted imaging, and it has a very excellent application in detection of stroke, the brain stroke, which is otherwise not possible to diagnose within short period of onset of the stroke. And then you can also use extend this technique to diffusion tensor imaging, where you can look at the white matter fiber tracts and see how they get affected when the disease process sets in, or when you are giving a training to a person to learn new skill. Anything you design your experiment, you can actually look at how the diffusion, these tractography, the changes happen in the white matter fiber tracts. Then you can also use, based on chemical shift, you can use the MR spectroscopy in different conditions. Coming back, I think I am sorry there will be some repetition because a lot of people have spoken about the NMR principles. So there may be some repetition, but next second lecture onwards, I think we'll be quite independent from what has been taught by the previous speakers. So you all know discovery of NMR was done in 1946 by Bloch and Purcell, working in two independent places, and they found that when certain nuclei were placed in a magnetic field, they absorbed energy in the radio frequency range of the electromagnetic spectrum and re-emitted this energy when the nuclei transferred to their original state. And they both shared a Nobel Prize for Physics in the year 1952. And to be NMR sensitive, or to be able to produce an image from any element, the element must have odd number of neutrons and protons. I think this all you must be aware of this, and should be abundant in the body. And hydrogen, because we have about 70% of our body weight is water, so water is H2O, so there is abundance of hydrogen atoms in our body. So it is a very excellent nuclei to be used for NMR experiments in diagnostic imaging. So there are several other nuclei which are of biological importance. The hydrogen, and then carbon 13, then oxygen 17, 19 fluorine, 23 sodium, potassium 39, and phosphorus 31. These are some of the important elements which are of biological interest. But in NMR, what we usually use is hydrogen, fluorine, and 23 sodium, and 31 phosphorus. These are the nuclei which are being used by various groups to perform imaging or the spectroscopic measurements. So I think this you must be aware about the spin, and then only elements which have odd number of protons or neutrons or both are NMR sensitive. If there's a equal number of, if the number of protons and neutrons are even, then the spin is 0, so they don't participate in the NMR experiment. So we also know any nuclei which has a spin half will have two spin states, which is gone by the formula 2i plus 1. If I is half, then there will be two spin states. So similarly in hydrogen, when you talk about hydrogen, it has one proton and it is spin half. So when it is placed in a magnetic field, this splitting of energy levels in the two state, it can be in two states. the lower energy state and the high energy state. So it has basically two energy states where it can be there. And the difference between the energy in two states is delta E, which is shown here. And this delta E will increase when you increase the magnetic field, applied magnetic field. More the field you apply, higher will be the delta E and higher will be the resonance frequency, which you must be aware by now. Then this is the again must be familiar picture for you. This is how the polarization happens when you place a sample of NMR sensitive nuclei into magnetic field. There's a splitting of energy levels, and the some of the nuclei they align with the field, and some of the nuclei they are anti-parallel to the field. And it is known that the difference in the population of the two states is just 1 or 2 or 3 in 1 million, the difference between the two population states. But looking at the Avogadro's number of water molecules in 1 gram of water, 10 to the power 23, molecules, they are still sufficient number of nuclei which can be used to perform the NMR experiment. And the equation is given here. The number of nuclei which are parallel and anti-parallel is given by this Boltzmann distribution equation, which is shown here. And then this was the and what happens in NMR experiment. You pump in radio frequency energy into the lower energy state nuclei and make them flip from lower energy state to higher energy state. And when they jump back to acquire the thermal equilibrium, they release the energy, which is the basic NMR signal. I think this is how by now you must have learned from the my predecessors. So, but the MRI is based, mostly explained nicely when you take a classical treatment. What was shown by now was a quantum mechanical treatment, but the imaging part can be very well visualized and learned easily if you look at the classical treatment. And we have this sample on the left hand side. You can see sample when there's no applied field. All these hydrogen atoms in our body they are randomly oriented, so there's no net magnetization in the body. So the net magnetization is 0. But if you apply a very strong magnetic field B naught in the on this sample, so most of the nuclei they will align with the the magnetic field, because all these nuclei which has hydrogen atom has positive charge and their spin, they all will behave like a tiny bar magnets, and these magnets will try to align with the external magnetic field, and all these vectors will add up to a bigger vector, magnetic vector, which is called m naught is equal to mz, and mz is the direction of the external magnetic field. So, and this is a convention in MRI and NMR. The direction of the magnetic field is always taken in z direction. So, and it is in the, like you have a magnet on the left hand side, so it is on the axis of the magnet. The z direction is taken in and out. So the other two directions, the sagittal and the coronal planes. So now, having said that, so once you have this magnetic field, when you create this vector, magnetization vector, net magnetization, when it precesses around the external magnetic field with an equation called our Larmor equation, which is omega naught is equal to gamma b naught, where b naught is the strength of the external magnetic field, omega naught is the resonance frequency or the Larmor frequency, and gamma is a constant, which is the ratio of magnetic moment to the angular momentum of a particular nuclei. And this gamma for hydrogen is about 42.58 megahertz per Tesla. So if you have a 1 Tesla magnet, so resonance frequency of hydrogen will be 42.58 megahertz. It's a linear equation. If you have 2 Tesla magnet, so the frequency will be about 83 megahertz. Sorry, 85 megahertz. So this is how you can calculate your resonance frequency due to this is the precision frequency. When you put this sample in a magnetic field, this m naught vector precesses around the axis of the magnetic field with Larmor equation. And if you look at the other nuclei, fluorine, sodium, P31 and carbon 13, they all have different resonance frequency at the same field strength at 1 Tesla. So the beauty of MR is that if you pulse at different frequencies, you can excite different nuclei from different elements. So this makes NMR all the more powerful, and you can do multi-nuclear measurements using MR and NMR. So once you have created this magnetization z-axis, so this is precessing around the axis of the magnetic field, which is the z direction, and then now this will keep precessing in this direction. Now we don't get NMR signal in this direction because there is a very strong magnetic field placed there. So what we do, we apply a radio frequency pulse, a 90-degree pulse or a radio frequency pulse, which will flip this magnetization from z-axis to xy plane. Okay, when it's flipped to xy plane, and then these magnets will start dephasing out because they have to go back to their thermal equilibrium. So there will be diffusing of these pins within the xy plane, and then this dephasing of the change in magnetic field will be sensed by a RF receiver coil, which is a tank circuit, basically LC circuit, which is tuned to the resonance frequency, and accordingly a current will be induced in this coil, receiver coil, which you call FID, free induction decay. And here's a cartoon which is caused by Faraday's law of electromagnetic induction. When there's a change in magnetic flux, there's a current induced in the coil. So same principle is applied here. When this magnetization decays in XY plane and it recovers back, so there's a change in flux which is sensed by this resonance circuit, and a current is induced, which is the free induction decay, which is a fundamental signal. Whether you are doing imaging or the spectroscopy, that is the signal you get out of NMR. And after this pulse is removed, so then there is a two processes which are happening to the system to achieve the thermal equilibrium. The M naught, which was shifted to MXY, will tend to go back to Z direction slowly, and also MXY will also decay in the XY plane. So there are two processes which are happening simultaneously during this process. So, and after you have FID, if you Fourier transform, then you can look at the signal which are shown. If there's a single component frequency, then you will see only one signal. If you have multiple frequency, when you Fourier transform, you will see multiple peaks appearing from that sample depending on the number of frequencies it contains. So this is I think this is just for your information. Gauss is the unit of measurement of B naught magnetic flux in CGS system, and Tesla is about 10,000 Gauss, and we know Earth's magnetic field is only 0.5 Gauss, and that means in the MRI you are using 30,000 to 70,000 or maybe more than that order of magnetic field compared to the Earth's magnetic field. So they are very strong magnets, and most of the magnets are supercon magnets which are always on. And for any NMR experiment, there are two type of pulses. I think this also you must have learned by now. There are two type of pulses: 90-degree pulse and the 100-degree pulse. These are the two pulses which are the backbone of any NMR experiment. And now these pulses can be non-selective RF pulses and can also be selective RF pulses. Non-selective RF pulses are used mostly in spectroscopy when you are not doing any volume localization. And these non-selective RF pulses will excite all frequencies depending on the pulse width. Okay, but the selective RF pulses are used in MRI because they select only band of frequencies which are contained into a particular slice. That's why they called size selective RF pulses. And so 90-degree pulse, 100-degree pulse, and alpha pulse could be any pulse which is from 0 to 90, which is also will come to these pulses when we go to imaging. We'll see how these pulses are important, which are not 90 but less than from 1 to any degree from 1 to 90. They are also very important in doing some of the faster imaging techniques. So this is how when we apply a pulse which can flip the magnetization M naught from Z direction to MXY plane, we say we have applied a 90-degree RF pulse. And if you apply a pulse of sufficient duration that this mz goes to m minus mz, then we say there's a flip angle of 180-degree pulse. So we say 180-degree pulse has been applied. So 90-degree pulse is called excitation pulse, and 180-degree pulse is called inversion pulse or rephasing or refocusing pulse in the MR experiments. So this is a nomenclature. Excitation pulse is 90-degree pulse, and the inversion pulse or the refocusing pulse is the 180-degree RF pulses. And how do you calculate the flip angle? Space flip angle or the tip angle is calculated by gyromagnetic ratio into B1 field, which is a radio frequency field, and time of pulse. So depending on this, you can calculate how much time is required, how much time the pulse should be on to create a 90-degree or a 180-degree pulse. For example, here we have taken an example. If you want to create if you have a B1 field of 2 microtesla, and we want to create a 180-degree pulse, so you need at least 5.9 millisecond pulse TP duration, pulse duration, to create this 180-degree transition from plus Z to minus Z direction. So if you recapture what we have studied till now, that means only elements with odd number of protons or neutrons are NMR sensitive. Example given is nuclear biological interest is hydrogen, carbon 13, fluorine, sodium 23, phosphorus 31. All these have half integral spin equivalent momentum except sodium, which is 3/2. In our body, millions and billions of such magnets of hydrogen are randomly oriented, and there's no net magnetization within our body. If you place this body in a strong magnetic field, there will be a net magnetization vector m0 in this z direction. We call it m0 is equal to mz, build up in the direction of b0, which is the external magnetic field at thermal equilibrium. By virtue of spin angular momentum of the spins, this magnetic vector will precess around the external magnetic field with the equation given by Larmor equation, omega naught is equal to gamma b naught. And we also studied that gamma for hydrogen is 42.57 megahertz per Tesla. Since gyromagnetic ratio of nuclei from various elements is different, so their Larmor frequencies will be different for the same field strength. The magnetization vector can be flipped from z direction to xy plane with the application of a 90-degree RF pulse exactly at Larmor frequency. And after the withdrawal of the RF pulse, the magnetization vector will tend to recover back in z direction due to a relaxation process. And this change in magnetization in xy plane will be sensed by a receiver coil, which is a tank circuit, LC circuit, and tuned to a resonance frequency of Larmor frequency. And then because of electromagnetic induction, voltage will be induced in this coil, which is the fundamental NMR signal, which is called FID. And the induced voltage decays with time as a function of transverse relaxation and is termed as free induction decay, which is a fundamental NMR signal. And till this point, when you get this FID, whether you're doing imaging or spectroscopy, everything remains the same. There's no difference in the two methods. So after having said that, after we apply a 90-degree pulse, we talked about that to achieve the thermo equilibrium back, there will be relaxation processes where this mxy will slowly come to zero and mz will recover back, m0 will recover back in mz direction. So there are two relaxation processes which are happening simultaneously. So this is how it is picturized. After you have flipped this by 90-degree, then this will tend to go back in a spiral form, and then it is going, and then after some time it will come back to z direction. The magnetization will come back to z direction, and mx will also decay completely to zero. So these are two relaxation times. One is called T1 relaxation time and the T2 relaxation time. This is how it is picturized here. When T1, after some time, after the 90-degree pulse has been switched off, the MXI will start dephasing out, and MZ will start growing, and after several T1 times, several times, the MZ will become M0. It will recover fully in Z direction, and also in the meantime, MXI will also decay to zero. So these are the two definitions of relaxation times, and here it is picturized, and you can see this is how this is exponentially building a function m is equal to m0 1 minus e to the power minus t upon t1. So t1 relaxation is a function of t1 relaxation time, and this is shown how this m0 is building up with passage of time, and at full recovered fully equilibrium state, mz will again become m0, which is the fully relaxation T1 relaxation. And in one T1 times, this is about 60.63% of the M0 is recovered in Z direction. So if you have to have a 100% recovery of the magnetic M0, then you need at least 5 T1 times. Then when you have 99.9% recovery of the magnetization. So for any experiment, you have to wait after you give these pulses, 90-degree pulse. You have to wait for certain time so that the system again comes back to the in the thermal equilibrium. So this is how we have shown. The graph shows the two exponential curves for two tissues which have two different relaxation time, and you can see they at the same T1 how they have recovered from two tissues have recovered at different moments. So similarly is the T2 relaxation time. This is a decaying exponential function, and it is mxy will decay as a function of m0 e to the minus t upon t2, which is t2 is the relaxation time. And here you are seeing that after the 90-degree pulse was applied, mz came to mxy fully, then slowly these spins will start dephasing out, and then when mxy becomes 0, so about 37% of the magnetism is left. So this is how the T2 decay is happening. And here you are showing the two different tissues which have different T2 times, how their contrast will change when you acquire a signal at particular moment of time. So when you go over a longer time, you can see the two curves have quite a difference in their recovery in their decay process, and then this gap of the two tissues can be visualized in MR image, which will be very clear when we look at the images. At this moment, I just want to tell you, when there are two tissues which have two different T2 relaxation times, how they will be, how their exponential curve will be shown, and how their contrast can be adjusted by doing the adjustment of the acquisition parameters. So the T1 relaxation time is also called longitudinal relaxation time or spin lattice relaxation time. And similarly, T2 relaxation time is called the transverse relaxation time or spin relaxation time. So there are three names for each type of relaxation processes. So this is I am showing in both on the same scale. This is a exponentially building up, and T2 is exponential decay curve, and so then they are governed by these equations. Now question is how the contrast, we get a contrast in the MRI. So there are only three type of tissues in our body. Either they are solids, liquids, or gases. And it is a great thing that solids, liquid, and gases, they have different T1 and T2 relaxation times because of the various physical processes. If you look at solids have very long T1 relaxation times and very short T2 relaxation times. They are as short as microseconds. So there is a beauty that in MRI you don't see a signal from the bone. So you don't see a bone artifact in MRI images because bones are solids and they have very short T2 relaxation time, and they decay so fast that it is difficult to pick up the signal in such a short duration. The reason for long T2, long T1 and short T2 of the solids is because the number of degrees of freedom, you see at the solids, it has only 1 degree of freedom. If you strike a solid, there's only one vibration, the way the energy can be dissipated in solids. So there's only 1 degree of freedom. So the relaxation process, the energy dissipation to the lattice is very slow. So that is why the solids have very long relaxation time. At the same time, since solids are very tightly packed, these spins are very close to each other. They can exchange energy within themselves. The downspin can exchange energy with the upspin, and they will keep flipping. So because of this process, the T2 reaction is much faster in solids. When you look at liquids have long T1 and long T2. So liquids have translation and rotation, both degree of freedom. So they are a little more efficient as far as the energy dissipation is concerned. And since they are loosely packed, the spins are not very close to each other. So it takes a little effort for spins to exchange energy and lose decay the decay of the signal. And similarly in gases since gases are short T1 and very long T2, and this is because gases have it can have all the type of degrees of freedom, translation, rotation, and vibration. So the T1 relaxation is very fast in gases. So the T1 is very short, while as since gases are very loosely packed, spins are much far away. So this exchange process is very slow, and they have very long T2 relaxation times. And if you have something semi-solid, semi-liquids, semi-gaseous, so accordingly these T1 and T2 will vary, and they will give you a different contrast in the images. So here the idea of this slide is to tell you that T1, if you go from 1 Tesla to 2 Tesla or 3 Tesla, the T1 relaxation of the tissues change, linearly. As as B0 increases, T1 also increases. And if you reduce the B0, T1 will also decrease. But T2 relaxation times are largely independent of the external magnetic field. So there are a lot of difficulties in creating T1 contrast in MR imaging systems when people shifted from 1.5 Tesla magnets to 3 Tesla and to 7 Tesla. So T1 contrast mechanism became quite difficult, and people had to work hard to set these contrast mechanisms right by trying out different pulse frequencies, and then inversion recovery pulse sequence became famous for this purpose, and many more changes are made so that T1 in contrast images can be produced in a nicer way. So is there any till this is the point where there will be some delay in slide transition. In the meantime, we can discuss if there is any query or questions in between. Can we use this time in that?
Yeah, yes, sir. So participants, if you have any doubt, you can ask the Professor Khusro at this stage before he goes to other aspect. Okay, participants, you can directly unmute your this mic, and you can directly ask Professor Khusro, or you can write your queries in the chat box. Anyone? Any doubt?
Shall I proceed further then?
Okay, I think no questions, but Professor Khusro, I have this silly question maybe for you.
Yeah,
This
please.
MRI contrast, it is based on this time scale of this relaxation.
Yeah.
It is in broad sense.
See, I told you there are about a dozen parameters we decide the MR contrast, but most of the diagnostic work is done using T1 and T2 based images.
On relative parameters, right?
Yeah, most of the images, yeah.
Okay, fine.
But when if you want to look at different disease conditions, like as I said, diffusion, if you want to look at a stroke, brain stroke, T1 and T2 images will be normal till several hours.
Okay.
They will show up only after 6-7 hours of the stroke. But diffusion, if you study the diffusion weighted image, it will show you within few minutes of onset. And
Okay. So you need to take help from other aspects also, right?
Yeah. Depending on what you want to see,
you
have to utilize all parameters of contrast.
Okay. Okay, sir. I think no participant has responded. So if you feel like you can continue, maybe.
So I am now introducing another relaxation time, which is T2 star.
Sir, one question. One question
Yeah.
maybe in the chat box. Can you read it?
In YouTube. I will.
In YouTube, or just copying it and putting it in your chat box. Can you see, sir?
Yeah.
It says biological system contain many paramagnetic metal ions. How it
Yeah.
affects the relaxation times?
Yeah, they do affect, like, most of the contrast agents which are used in MRI, they are based on paramagnetic ions. So they reduce the T1 relaxation time, and they can also reduce the T2 relaxation time depending on the type of contrast you are using, type of paramagnetic ion you have. If you are using a gadolinium type of paramagnetic ions, they reduce the T1 relaxation times to enhance the pathology. And if you are using super iron oxide materials, then they will reduce T2 relaxation times, and they are called positive contrast agents and negative contrast agents. So I think they do affect the relaxation times. Yes.
Yeah. Okay.
That is the purpose of using contrast agent in MRI.
Okay, sir. Okay. Thank you, sir.
Any other question?
No, I think you can go ahead.
Actually, I like this to be more interactive, so that
We also want that way, but most of the time participant doesn't interact spontaneously. Maybe
Okay,
they,
but I have given my email address.
yeah,
Any
they may be,
participant, if you have any query, please let me know.
hopefully
We can, and I can collect all questions by email, and then maybe next lecture 5 minutes we can use to answer those questions.
okay, thanks. That's fine, sir. Yeah.
Now, when we are talking about T2 relaxation time, we are talking about the intrinsic T2 relaxation time of the tissues or the nuclei. But when you are using when you are looking at the T2 relaxation as a process as a whole, there are several other components which affect the T2 relaxation time. Like somebody was asking about the paramagnetic ions, they also affect T2 T2 relaxation times. So we call T2 star relaxation time is equal to 1 upon T2, which is the intrinsic relaxation time, spin relaxation time. Then 1 upon T2m, which is the contribution, the decay of T2 because of the inhomogeneities in the magnetic field. Because you all know we are producing such a huge magnetic field, we don't expect magnetic field to be exactly uniform at every point. There will be some minor ppm or ppb level differences in the magnetic field, which will also cause T2 relaxation, decay in the T2 relaxation. So we call it T2m. And then the third part is the magnetic susceptibility, which could be because of the paramagnetic ions or the blood products or the blood, or iron or any other deposits of the metal deposits in the tissue. So they all contribute. So we call it 1 upon T2. We call it T2 star relaxation. And you can produce images of T2 star relaxation also by using appropriate sequences and using appropriate parameters. So you have now, you got proton density contrast, you got T1 contrast, you got T2 contrast, you got T2 star contrast. So 4 contrast parameters you know by now. Am I okay? Hello?
Yeah.
So,
Fine, sir.
okay. So, people who are in chemistry and, who are in developing of contrast agents, they prefer to use relaxation rates and relaxation times. The R1 and R2 are just, inverse of T1 and T2 times, and they use this terminology quite often. So I thought I must tell this gathering that there's a term called relaxation rates also, which is being used by chemists while they, develop the contrast agents for MRI and NMR. So you can see on the left hand side is a water, gray matter, muscle, liver, how different they have T1 and T2 relaxation times, which causes them to have different contrast on the MR images. This is a sort of a, you can see ice, which is water. When it is in solid form, it has T1 of 5000 milliseconds. When it is T2 relaxation is just 0.001 millisecond. You can see how short T2 time it has. So it is very difficult to produce images from constituents which have very short T2 times. particularly the bone. So these are some important points. Fat has a short T1 recovery time, and fat has a short T2 decay time. Water has a long T1 recovery time. Water has a long T2 decay time. Free liquids, water, etc., they have long T1 and T2. T1 recovery is caused by spin lattice energy transfer. T2 decay is caused by spin energy transfer. The efficiency of this process depends on the inherent energy of the tissue and how well the rate of molecular tumbling matches the Raman frequency. This is what we spoke, how quickly they can release their energy to the environment or to the lattice. The efficiency of the process depends on how closely the molecules are packed together. As I said, like solids are tightly packed, so T2 is very short. Liquids are not so much packed, so they have moderate T2, and gases are very loosely packed. They have very long T2. So T1 recovery times are dependent on magnetic field strength. As the field strength increases, tissue takes longer to relax. T2 decay times are not much dependent on magnetic field. They are fairly independent of external magnetic field. T1 contrast is controlled by the TR. T2 is contrast is controlled by TE. These are the terms which I have not discussed this, but I think because of these previous lectures, you may be aware what is TR and TE. But we'll come into detail when we have subsequent talks on the imaging. For good T1 contrast, TR must be short, and for good T2 contrast, TE must be long. I will tell you this again next time why this characterization is done by you choosing the appropriate times of acquisition of the parameters or the images to produce a certain sort of contrast. So we have some time. We can continue with the next talk for 5-10 minutes, or if you have any questions, we have 5 minutes for discussion, 5 to 7 minutes for discussion. And these are, for your reference, these are 3 NMR machines. On the left hand side is a 3 Tesla human MRI system, and which was there at INMAS where I worked till 2019. And on the right hand side, this is a 7 Tesla animal MRI from Bruker. This is a 7 Tesla, very powerful magnet, and it can do micro imaging. The resolution can be of the order of maybe 100 micron or so. And this is essentially for imaging of small animals like mice, rats, and maybe rabbits. So this is a very good machine for doing translational research for drug discovery and drug trial experiments on the animals. In the center of the 2 imaging machines, we have a spectrometer, NMR spectrometer, which can be used for doing NMR spectroscopy of liquids and tissues, or in vitro samples, whatever you want to do. And this is a major application now of this spectrometer is in NMR metabolomics, where you subject the urine or the serum or saliva or any body fluid to the NMR experiment to detect the disease, and have biomarkers or fingerprints of a particular disease condition. So this is, I thought I must show you these 3 systems so that you understand. People who have not seen MRI, at least they can have a glimpse of the machines, how they look like. Of course, when we have instrumentation lecture, we will discuss them in more details. So what is your opinion? Shall I switch to next lecture, or
okay,
we have discussion?
Yeah, you can stop it. Just let us see if any participant is having any question.
Yeah. Please ask questions so that I also feel comfortable.
Try to interact as far as possible.
Yeah, let the question be any, no question is,
every question is question. Everything is
every question,
learning.
and it will give me also learning.
Yeah,
Because
don't
somebody
hesitate
very rightly raised its paramagnetic ion is going to affect the T1 contrast, the reduction times. Yes. So that is a very good question actually. I solicit good questions like that, or any question which arises on your mind.
Anything, any doubt,
Anything, yeah.
So participants, try to utilize the time.
And if somebody is shy of asking questions, please write down on the email or
Yes,
So
email, that
next,
option is also open, so you can write Professor Kusu at his email ID. He will be happy
yeah,
to answer your questions. Okay. And Dr. Professor Kusu,
yeah.
this reading materials, this your presentation, can you share with the students in maybe in
I will do one thing. You know, after I finish, I will send you slides, the teaching
I-
slides to you.
yeah,
You can then you can pass
it
it
will
on to them.
upload to in our website.
And do they have any access to any book, NMR book, MRI book?
Book, maybe personal level, they are maybe consulting, but from our side, there is no book as such. What we are providing is the lecture note.
Okay,
So,
what I will
in
do, I will send you a PDF.
PDF form, you can send it to in the PDF form so that you can share it with the participants.
I can share with you a PDF book, small book on
All
imaging.
right.
There's a basic, there's a very basic book and very easy to understand.
I can share it with the
Yeah,
participants.
yeah, you can share. There's a sharing. There's a contrast agent company, no?
Okay.
They had made a small book for medical practitioners, doctors, and
Okay, fine.
it is on net. I can share. There is no problem.
Okay, sir. Then please share it with me. So I'll.
They can just read that. No need to take a printout and all that. They can just for reading purpose they can use it.
Okay, fine. That will be
Okay,
nice.
that will be nice for them to understand the
Yeah.
basic
From
concepts.
reading material, they need to at least they can go through repeatedly so that it's naturally new for each of us. So
Yeah.
we need some reading material to go into the details, right?
But I will love to have more interaction on the lectures.
That I also try to insist our participants to make
No,
more
because
interaction.
actually what happens, the concepts of NMR, though they must have gone through for last several weeks, they are undergoing NMR lectures.
Share this email ID.
Basic principles they must be already aware.
So for
But this,
everyone,
yeah,
I have shared my email ID, so you can write to me.
I
Uh,
have your email ID
Yeah,
already.
for participants also, you can write your
Yeah,
doubts to me as well if you are
yeah,
hesitant. Okay,
okay, that will be nice. Yeah,
okay, so that I can share with Professor Khushu.
yeah,
Okay, but I will prefer you directly write to Professor Khushu. He will be more happy than going through me.
yeah. I know. I think anyway,
No, but
I will be happy anyway, provided they ask questions.
right, right. Okay, thank you, sir. Thank you very much.
Was I very fast?
No, it's okay, fine. I think it's going normal speed. This is okay.
Actually, now next lecture onwards will
Mhm.
be quite different from what they have learned through NMR. Because I will be now going on basic image formation and concept of magnetic field gradients and how you specially encode the signal. So this is a little more
Yeah,
tricky because because it has to be a long duration course in person. But since we have very limited time,
yeah,
so I will also only like them to appreciate what MR can do in their field of research.
correct. So it is a basically we are trying to give an introduction to the MRI so that people get interested in the topic. That is the
Say
main
it
purpose.
again. Say it again.
Our main purpose is to introduce the topic
Yeah,
so
yeah.
that interested people can get into it.
Can research
Usually,
further. Yeah,
major
that's
things
true.
cannot be covered. It's a short duration course is not possible to cover the whole thing.
Yeah, I know. And this field is so interesting. I think everybody, if they if they learn, understand, most of them will get interested in this field. It's such a
Right, right.
wonderful area.
Because we by term only we know MRI, but what MRI is doing, we don't know anything.
Yeah, yeah, yeah.
So that curiosity is the driving factor for all of us.
Things will get easier when we go to applications. Things will get
Yes,
easier and more interesting.
right, sir. Yeah. Okay, sir. Thank you very much.
And I'm sorry for this trouble with the slides in between.
That is okay. It happens. You don't bother. It happens always. Okay, we'll manage with it.
Yeah.
So our next lecture will be on Wednesday, same time,
Day after tomorrow. Yeah,
day after tomorrow. Yeah.
yeah.
Okay, sir. Till then.
Thank you so much. Thank you so much.
Thank you very much. Till then, bye. Bye.
Yeah, thank you. Thank
Thank
you.
you.